Okay. A minute ago, we just calculated how much, what the final temperature would be if we added 30 kilojoules. And we noted that it would take 33.4 kilojoules to melt the ice, and the final temperature was at 0. So now we're going to raise the temperature to 70, the heat to 70 kilojoules, okay? So we know that if we add 70 kilojoules, the first 33.4 kilojoules would be used to melt the ice. So 70 minus 33.4 is equal to 36.6 kilojoules. Now we have to ask ourselves, is 36.6 kilojoules enough to raise the temperature to the boiling point? Okay? So we know that the freezing point of water is 0, which when we melted the ice, it's at 0, and the boiling point is at 100. So we theoretically ask ourselves how much energy was required to bring this water to the boiling point. So we could go Q is equal to the mass of the water. We're going to use this equation right here, times the specific heat capacity of liquid water times delta T. So Q is equal to 100 grams times 4.184 joule per gram degrees C times the temperature change, which would be the final temperature, 100 degrees, minus the initial temperature, 0 degrees. And we do this, we see that it's 41.86 kilojoules. What does this tell us? This tells us that we have liquid water, and the final temperature is somewhere between 0 and 100 degrees, because we would have had to add 41.86 to bring it to the boiling point. So we know the final temperature is less than 100, and we have liquid water, okay? So now we ask ourselves, what is that final temperature? So we go Q is equal to MC TF minus TI, and we want to solve for TF, okay? So we divide both sides by MC, and we have TF minus TI equals Q over MC. So TF is equal to the initial temperature, I bring this to the other side, plus Q over MC, which is equal to, we started with pure ice. It took 33.4 kilojoules to melt it. Now we have ice at 0, we have water at 0 degrees C, and we're going to add an additional 36.6 kilojoules, because 70 minus that to melt means we still have this much energy we've added. So we add to this 36.6 kilojoules, and then we divide by the mass, which is 100 grams, and the specific heat capacity, which is 4.184 joules per gram degree C. And then we notice that we have kilojoules in the numerator, joules in the denominator. So we could go over here and we could say that there's 1,000 joules per kilojoule. And this gives us a value of TF equal to 87.5 degrees C. And this makes sense. If it took 41.86 kilojoules to raise it from 0 to 100, and we only had 36.6, we're roughly 87 degrees of the way there. And we could add it a little bit more and brought it up to 100. Okay? Thank you. All right.